assume you've all used something that communicates at some point in your life. You know, wireless techno doodads that do all the fancy science and the thingies. And if you've ever like messed around with like, you know, essentially what communication frameworks are doing is imagine a flashlight from really far away and flicking it on and off really fast, and someone far away has to write down what you're flashing and convert that to a message. And this is very bad. Like, a lot of errors happen in this process. And that's not good, because like, oh, I can take my mask off. Ha, I'm powerful. Anyways, a lot of errors can happen when you do this, because, you know, obviously, and that's bad, because obviously. So it's a good goal to try and minimize the number of errors you have while communicating. Unfortunately, that title is actually an error. In general, it is very hard to come up to find ways to minimize errors when communicating, specific algorithms. But we do, surprisingly enough, know a lot more about what is hypothetically possible and what is hypothetically not possible. So there's two ways to minimize errors during communication. It's to make the framework better, or to actually change what you're sending in such a way that it's more resilient to error. And we're going to talk about the second one today. In order to do that, we need a mathematical model, because physical objects are a little bit outside of our pay per view. We are math students. And so I'm going to motivate a notion called a channel, or Shannon Channel, for those of you who know that name. That's an example of a Shannon Channel. And what are the key elements? Well, there's an alphabet on the left side, 1, 0. Alphabet on the right side, also 1, 0. And then we get a probability distribution for output. So I start with 1, and there's a probability distribution for what you're going to get on the other side. So there's a 1 minus f, like say f is 20% here. There is a 20%. There is an 80% chance you get a 1, and a 20% chance you get a 0 if you start with a 1, and then you flip it around. It works the same way. So this is good. And if we were just to use this channel verbatim, you would do something like this: send 10 zeros and 10 ones. You send them over your channel, you get 10 zeros and 10 ones on average, but you know, some of them got messed up. Like that one should be 0, that one should be 1. And here, you get an error rate of 20% with a channel that flips 20% of bits. But there's a very, very trivial way to reduce the amount of errors that you see here. And yeah, you'll want to fix it. Ignore these slides. What you can do is you can what's called a repetition code. It's the most trivial form of error correcting code, where you take every bit, you repeat it twice, you send it through, and then do majority vote on the other side. So here, there was an error in the block, but we can correct it, and then we're good. It's like nothing happened. Unfortunately, we could be unlucky and get something like this, and the bit ends up getting flipped. So we decode something different. But despite that sad eventuality, we still cut our error rate in half, from 20% to 1.04%. But there is a trade-off. Before, we were sending 1 bit per use of the channel. Now, we are sending 1 bit for 3 uses of the channel. And this means that our code rate, which is the number of bits we get per bit we send over the channel, is now a third. And so we're seeing this kind of trade-off game where we increase we decrease the error rate, but then also we decrease the code rate, and you can't really get both of them high at the same time. So, you know, you can imagine the space of everything possible, right? On the one axis, I have the rate. The further you go, the less information you're sending. The other axis has the probability of error. The further up, the more error you get, and you want to end up somewhere down here. And that's the repetition codes. You can see a nice function leveling off to the origin. Cool. And one can ask, hypothetically, how good is possible? Where on the diagram can we get to? I'm going to spoil the whole point of the talk. And here. And now. This line doesn't go through the origin. This means it's possible to get an arbitrarily low error rate while still getting a certain amount of communication across. The constant here, at which it hits the x-axis, is called the capacity of the channel. And the most important thing to note about Shannon's result is that that is not 0. Shannon's original proof is broken in 3 parts. It's broken into this part, this part, and this part. This is the interesting part. That's all we're going to talk about. So, yes. here's the official statement for part 1 of the theorem. For all error rates, epsilon greater than 0, encode rates are less than the capacity, which we'll define later. There exists a coding and decoding scheme that exists with error rate epsilon and code rate r, or better than those two. Now, I know that you're all dying for the proof of this theorem. I am not going to give it to you. I'm going to go talk about binary search. I assume some fraction of you took like 136 or something, like you know code, right? Code and stuff, computers. And so the basic idea of the algorithm is that we can do a test to see if our number is greater than some pivot or less than some pivot, and we can knock out half the search space each time. So I want to ask, is my number less than 32? Nope. There we go. Cut out half the search space, and I can do it again, and eventually we'll get to our number. Wonderful. And so what did we learn? First, well, we cut the search space in half when we did our comparison. That's good. But then if we look at the binary representation of x, we actually got the first bit. Because if it was less than 32, then the first bit is 0. It's bigger than 32, the first bit is 1. So we got 1 bit of x. Now I'm going to introduce a variation of binary search called trinary search, or ternary search. I don't know what the actual name is because I made it up. And we're looking for x within 0 to 80, which is 81 minus 1. And we're going to play the same game. We're going to cut our interval into 3 blocks this time, and we're going to ask which block are we in. Right? And so here, we were in the top, not in the bottom, not in the top, some in the middle, boom, smaller. And so we can ask ourselves, what did we learn? Cut the search space in a third, but then there is no nice analog of how many bits we got of x. Because we got a little more than 1, a little bit less than 2, we didn't cut it by half. So we're going to define, there is like a way of making it work. We can take log is log base 2. Yes, because it is. We got log of 1 over a third bits, right? And if you plug in a half for where the 1/3 is, you'll get 1 out. If you plug in a quarter, you'll get 2 bits, and you kind of see where the definition came from, right? If you just plug in a bunch of values, the curve makes sense. So if we cut our search space in third, we get 1 over a third bits of information, let's say. And this is nice because it's a bit number, and we can compare things. We have a consistent unit of measurement. So this is what I call the Shannon information content. H of an event x is 1 over the probability of that event. That's cool. Now there's another question. This is a question I had when I first learned about binary search, all right? This is just a fun property. It's additive. If you have 2 independent events, the probability is a product, so information is additive, right? If you do 2 tests, you get 1 bit, you get 1 bit, you get 2 bits, right? Anyways, so you know how in binary search we cut it in half? I'm a bit of a gambling man, right? Instead of cutting it in half, what if I cut it in a third and 2/3, all right? I know that 2/3 of the time you're kind of stuck, so you got a large search space, but 1/3 of the time you get a much smaller search space than you would with binary search. So, maybe gambling is actually the best way to go instead of playing it safe. How do we know that one is better than the other, and why is the half so much more popular than pseudo-trinary search? Well, what I can do is I can take the expected amount of information I get out of a measure, right? I mean, the more information you're going to get on average, the better your algorithm, all right? So here, there's a 50% chance I get 1 bit of information. There's a 50% chance I get 1 bit of information, and so I get 1 bit of information on average, right? That's the expected amount of information. If I measure the expected amount of information for pseudo-trinary search, there's a third of a chance I get log base 2 of 3 bits, and 2/3 of a chance I get log base 2 of 3/2 of a bit. And that sums to something that is less than 1. So therefore, I have proved through the power of math that binary search is the correct way to do things. It also points to a useful idea. Entropy is the expected amount of information for an experiment. So if I take an experiment, well, really I need a random variable. I need to know the probability of each of the things that you can get out of it. And then I can do the amount of information you would get if that were what you get. So cool. We can divide that 3. Now I'm going to go on a very hard tangent. I would have liked to smooth this over, but I was finishing this talk 2 hours ago. So, we have investigated random variables. Those are cool. Now, I want to talk about strings, and trust me, this actually does relate to communication. This is the last piece of random nonsense I'll have to define before we can talk about communication. We're going to talk about random strings. So I have a random x, and it follows a probability distribution. I define a string as a bunch of samples of x in a line, and each one of these things are independent of the rest of them, and they're all identically distributed, right? Now, if you think about the amount of information, I took the information of one random variable, or one outcome. I want to talk about the information I get out of a bunch of random outcomes, a string of them, right? And it's actually a little more convenient to look at the amount of information I get divided by the length, right? And the reason we can do this is that what we really are taking is we're taking the information with respect to x1, which is a random variable, the information with respect to x2, which is a random variable, and divided by n. This is actually sample mean, right? And for those of you who took statistics 230, 240, that one, right? I think it's the central limit theorem.
Yes.
Yeah, that one. Yeah, whatever. We get to a normal distribution, right? And the mean of the normal distribution. Well, okay, so these are all independent, identically distributed variables, and the theorem says that what you end up getting is the mean is the expectation of this variable. But the expectation of information is entropy. So therefore, we get a normal distribution centered at the entropy with the variance equal to variance, right? And the thing to note about the variance is that there's a division by n there. So right, we get a tighter bell curve as we increase the length of our string. And so now, why was the heading typical sets? Because I can talk about the set of all strings, and I can define the amount of information in a typical string, right? And so I'm going to define a typical set with some tolerance beta to be the set of all strings who have an average information content pretty close to the entropy, right? So basically everything at the center of the bell curve, and with a little band of tolerance with 2 times beta, right? And in the end, we're going to tighten beta small, right? And the thing to note is as we increase n, our bell curve gets tighter, and so the probability that if we pick a random string according to our probability distribution, that we pick a typical one tends to 1 as n tends to infinity. Bell curve middle. So here's that in bad notation. So now we can ask, okay, so it's weird to think that we have a set where most of our, like when we pick a string at random, we land in the set, right? It's tempting to think that that set is like just the whole thing, right? Because if we're tending to probability 1, you would expect that the set size grows to the whole set. And so we can investigate this. If we take any element within our typical set, we know the amount of information because in the set, it's the entropy plus or minus some tolerance, right? And so similarly then, if we can invert this is an equation where entropy, the information content of x is equal to 1 over the probability of x with a logarithm slapped in front of it. And so I can invert that to get that 2 to the negative information content is equal to the probability. And so therefore, if I take the one of the endpoints of that interval, I can lower bound the probability of getting my string, right? So if I pick a random string, I have a lower bound on the probability that it is one of the strings in my typical set. So now what I can do is, okay, if I take every string in the typical set, and I take the probability of drawing that string, and I add those all together, that number should be less than 1, right? Because you obviously can't get more than 1 with a bunch of mutually exclusive events, right? You can't have a probability more than 1. And so I can manually plug it in, and then of course I can multiply through by the probability, and then I can drop the beta term because that actually just weakens our bound. And so the size of our typical set is 2 to the n times the entropy of x. And notice that if we have a very, very skewed, very small entropy, and what that means is we have a very skewed probability distribution, some things are way more likely than other things, we're going to get that the size of our typical set is actually substantially smaller than the size of the full set of strings. Oh, and when I say 2, that's because we're doing binary strings, so the size is down. But yeah, you guys got it. Here's 1, right? And so now I'm going to teach you the real trick that actually locks up communication. we kind of introduced in the beginning when I talked about repetition code, but instead of focusing on individual bits that we're sending back and forth, we're going to focus on code words, right? These are groups of bits that we will have some common meaning, and then we have the same idea where we have a channel, we send it over, we get a probability distribution on the other side. And then when it comes to decoding, we don't have to, like, I don't have to say, okay, 1, 1 goes to 1, 1, 1. I can be a little more lossy in the amount of information I use. And say, look, I'm only ever going to send 1, 1, and 0, 0, right? And if you get something in the top half, that's a 1, 1. If you get something in the bottom half, that's a 0, 0. Or whatever coding mechanism you want, right? I can pick and choose. It doesn't have to be good, but I can pick them. And so now I can actually give you the idea of how we're going to prove this theorem, right? We have our code words on the left, and they each have their own probability distributions on the right. And I can pick a set of smart code words, hypothetically speaking, such that if you look at the probability distributions, I can say this is like a typical set, and these typical sets are, relatively speaking, disjoint. And if I send that code word, you're probably going to end up there. And so if you end up there, just decode it as that, right? And a similar type of thing going on for the rest of them, right? So if your output string is typical for a given input string, then you decode it as that. Plain and simple. So here's all of that math. We're going to fix our probability distribution for x. Like, we have our input. We can choose it however we want. And so I can fix a probability distribution, and it's wonderful. And I'm going to fix a rate because of the fact that there is a rate component that we're going to need, right? So I fix a rate, and note that rate is less than 1, by the way, because third before. So when I say 2 to the n or 1, there's actually some subset of the total number of code words, and so I pick some subset from the total number, and I pick these randomly, right? And if I pick it randomly, then what I really have is a bunch of independent, identically distributed variables, right? And these are known to the sender and receiver. The sender and receiver know the entire thing about the coding schema, right? Then on my side, I'm going to send a message over to Evan, and I'm going to choose a signal S, and that has a corresponding code word, right? Because S is one of our 2 to the n minus r things, and so that is a code word that we're going to send over. And then let's say Y is received, right? And then I'm going to decode what I get as S hat, if S hat and Y are jointly typical, right? So that's very similar to the definition I gave before, but I just extended to 2 variables, right? And it's so similar that I actually barely didn't even feel the need to explain it. And then, of course, the probability of error can be computed by saying if there are multiple S hats or there are no S hats. So, error probability, right? Let's say we send a message and we get the message S hat and we got error. One of the two is not jointly typical, or there's multiple jointly typical links. And so we're going to examine the first one, and I want to invoke this memory of what it means for 2 sets to be typical, right? Or at least a fact about typical sets in general when we were looking at one variable cases, right? The probability that you land inside your typical set is really, really high as we grow our thing. And so note that I can kind of define a 2-variable probability distribution, pxy, with the probability of x and the probability of y given x, right? Because that's exactly what we're doing. We're picking a code word with some probability, and we're picking another received code word, again, with some probability based on the original thing. And so what I can do is, when I define a random variable, I never said it had to be a number. I can make my random variable take on the value of strings of pairs of numbers. And so what I can do is I can find these pairs have a probability distribution, and so I can find the typical sets of these probability distribution, and I say x1s and y are jointly typical if the whole thing is a typical string, right? With respect to the probability of yx. And this, just with the lemma that we proved before, it goes to 0. So the likelihood of you picking a non-typical joint pair of strings gets arbitrarily low. Right? And yes. And so then this is the other half. Y is jointly typical of both x and c. This is the foundation of all coding theory, and I'm cutting it from the top, so I am debating you a bit, and I am sorry. But in my defense, I am, right? But I can tell you the techniques that Shannon used to prove it without going into the actual algebra. So what I can do is that it's very hard to analyze this probability in any specific coder. Like if I give you, hey, this is a generic coding scheme, tell me what this probability is, it's very difficult. So what Shannon did is look at the average case. He summed up over all encoding, decoding schemes of a particular subclass, and he said that the average is, he found that, where this is actually the capacity of the channel, which the capacity is really just a bunch of entropy functions that come out from the algebra. And beta is the parameter by which we define our typical sets. And notice that if the rate is less than the capacity minus beta, beta can be made arbitrarily small, so whatever you want to get. If the rate is less than our capacity, then increasing n also causes this probability to go to 0, right? So we have two probabilities of error. We know one goes to 0 because of typical set nonsense. You're going to have to take my word that the other probability goes to typical set nonsense, and the whole time the rate doesn't change. We fix it, right? So and if we assume that the rate is less than the capacity, we can get the error rate as low as we want it to go. So this is Shannon's Shannon code theorem, but the actual theorem, I took out the code word part just so that you understand what the trade-off is now. You have to make really long code words in order for this to work, right? Meaning ever more complicated code schemes. Now, Shannon's proof was not constructive, meaning that he didn't provide any mechanism, and so there is a whole field of mathematics called coding theory to find these kind of encoding and decoding schemes to get ourselves lower and lower on that plot, right? But then you know it's harder and harder to find the larger the n gets, right? So I know I kind of debated you by taking out the most pivotal part of the whole talk. And so I would like to recommend the textbook, which I binged in order to Bruce's talk. I figured it out pretty quickly. I'm certain that you intelligent people could figure it out equally quickly, especially now that you have the intuition that I gave. It's a really good book, lots of fun. And it is based off of this book. There is a lecture series by the same person. This is like if you Google information theory on YouTube, this is what will come up. And it is good for good reason, right? It is a wonderful lecture series. But yeah, that is all I had to present. Thank you for listening.